Good morning, everybody. Hopefully you can hear me. Could somebody say something or, I don't know, do something in the
I
chat
can
just
hear you.
to acknowledge that you can hear me? And also you should see the first slide that says use well CBW4. Is that correct? Can you see that? Okay, everything is working. Good. All right. So, I want to start off by making some adjustments to the slug test field exercise, just a small adjustment. When we met in the field, we were right here. Let's see, I don't know, right in there, and we were using that well right there, CBW7. CBW2 was the one that looked kind of like this with the plastic cap. Um, what I want you to do is measure the water level in CBW2 because you're going to pair that water level measurement with CBW7, and that will give you a vertical hydraulic head gradient. But for doing the slug test and estimating the hydraulic connectivity, what I want you to do is use this well here, CBW4. It's 100 feet between CBW2 and CBW4. And I cleaned it out, and this is what it looks like here now. So you should be able to find it easily there. See that white flag? That should be visible. That thing right there, that's the box containing the water level meter. Okay, so come down here and use this well to do the slug test. Uh, the permeability is a little bit higher here, so the slug test will go a little bit faster than this one here, and I think that'll help out. I when I was making this adjustment yesterday, I put this board here over CBW2. That's CBW2 right there, and it says, I don't know if you can read that, but it says use the other well. So what it should say is use the other well for the slug test, but still measure the water level in this well. So just move that board over, and there's the cap right there. You should be able to get in and measure the water level. Okay. So I think there's a group that's going out. Maybe they're out there now or going out there soon. And then I think today is a busy day in the field, so just wanted to make that adjustment. This well here should take. I was testing it out yesterday, and it should take about 25 minutes to come back to about 90% of the initial head change during the slug test. And when it gets there, then that's going to be that'll be close enough to recovery to start the slug out test. Okay, so the overall slug in and slug out is going to take about an hour. And that's why, we have this spacing of hour and a half, or really better 2 hours between the slug tests, so we can get that one fully recovered back to its initial water level before the next group starts. Okay, so any questions on that? Okay. So I'm going to continue on with our discussion of flow in the vadosome.
There's a question in the chat for you from somebody in group 4.
Wait a minute. So, yeah, so I just noticed I have my speaker unplugged. So were you able to hear anything the last few minutes?
We have been able to hear, yeah.
You have. Okay. I was not able to hear you if you were saying anything. So if you were saying something, then say it again. Were you saying something? I heard kind of a murmur there, and I realized that
I had just mentioned that somebody mentioned in the chat that group 4 had already tested with the previous instructions.
Yes, I'm aware of that. And group 4 can proceed as using their data. They tested CBW2, and that's fine. That test went a little bit longer than I was expecting, so that gives them a good data set for lower permeability. But just to kind of, because we've got so many groups going today, it wasn't really. It takes it. Just in the interest of time, I'm going to move to the other well. One of the things too that came up with the group who did the original test on CBW2 is that the slug test can last a long time. And typically when you're in the field, there's a finite amount of time that you can be there. So one of the things that is done is to, ideally you run the test till you get to 90% of recovery. But if that's not possible, then you terminate the test and take the data that you have and extrapolate it. So if you only got 50% recovery, but the data still plots as a straight line on the semi-log plot, you can extrapolate that to 0.37 recovery, and then for the Jacob or for the Bauer and Rice analysis, you extrapolate all the way down to 1 full log cycle of recovery. Okay, so that's possible to do, and that's something that you need to do when the permeability is really low. And so I think the group that was out yesterday was going to do that for their slug out test. But if we switch over to CBW3 or CBW4, then I think we can just run a complete test. Okay. Any questions about that?
So yes, or I believe I might be mistaken, but are we supposed to test CW7 and CW4?
Yeah.
For slug test, and everything else is just water level?
That's right.
Okay,
yep.
Thank you.
CBW7 is in the aquifer, and it'll go really fast. The group that was out yesterday, how long would it take before CBW7 was recovering? Maggie, I don't know. You there? I know you were out yesterday.
They said less than a minute in chat.
Yeah, okay. Less than a minute.
Yeah. So it goes really quick. So you have to practice and get really quick with the water level meter. But then up in the confining unit, it's slower. And what seems to be the case out there is that the permeability of the confining unit gets lower as you get further away from the Seneca River. So if we were to test that CBW1, the one where there's an upper and lower, if we were to test that site, we have done that in the past, and that takes, I don't know, that takes all day to recover, or maybe even more than a day. So it's really tight, and then it gets progressively higher permeability and quicker to recover during a slug test as you go towards the Seneca River. So we're gonna move in a little bit closer for the test. Okay, any questions? More questions? I see. I'm just looking at the. Okay, so timing problems I see in the chat. Yeah, maybe we can talk about that if there are timing problems. Well, yeah, I don't know. Joey,
let's just, the timing problems will, we've got multiple groups going. So what's the timing problem that your group is having?
I think we were supposed to be outside at 3:30, but
Yeah.
somebody in the group has an advising appointment at 3:45. So we were wondering if you either have the list of everyone's timings, so we could see if we could work around some other time, or if we could simply, I think there's a group going out at 1:30, if we could go out and do the tests with them.
I mean, you can do the test with them. It only takes 2 or 3 people, right? So if you have 5 or 6 people, then you're going to have people with just watching and not actually really getting hands-on experience. That was the reason for the size of the groups, because I'd really like people to get some experience using the water level meter and participating. So
Yeah, I would also like to do the test myself. It's just if we cannot get another time slot that would work for our whole group.
how many people? Well, okay, so there's one of your group members that can't go.
Yes. So we have 2 remaining group members.
Okay, well, so why doesn't that group go, and the person that can't make it can go with another group rather than the whole group change? So 3 people, there are 3 people that could go at 3:30.
No, just 2. Just me and one other person.
Okay.
There was another member of our group, but they haven't been to class and they haven't responded to my email.
I understand. Okay. Let's talk about it after class. I think that there are a couple of things that we need to get worked out. But I think probably that we'll have the 2 of you go, maybe with a third person. But I need to talk with you and some of the other folks to get things straightened out. Okay. I don't want to
All right,
take class
sounds good.
time for that at the moment. Just, yeah, too many moving parts. Okay. So what I want to do now, to get back to the topic for today, we're in the Veda zone, and what we were looking at yesterday, or I guess now Monday or Friday, was the pressure in the Veda zone. The pore pressure is less than 0, and it's negative, and that follows from, I think it would make sense that the definition of the water table is that the pressure equals 0, and the pressure increases when you go below the water table, and so it decreases when you go above. Just, conceptually, that makes sense. We saw a couple of examples showing more quantitatively that if there's no flow, if everything's just in equilibrium, then the pressure head will equal the negative of the distance above the water table. So that all makes sense and follows from some basic principles. But the question is then, why does it happen like that? If we're here at the water table and the pressure here is 0, then we go down and go down below the water, and you can think of it as the weight of the overburden is causing the pressure to increase. But then why does the pressure decrease when we go up above the water table? So the way to address this question is to look at what's going on right here. This is in a capillary tube. This is there's a curved meniscus that's this surface here between the water and the air. And if I blow that up a bit, then it looks like this. So it's curved, and there's water molecules here and air molecules here. and the traction between the water molecules is down here. There's a traction between from one water molecule to neighboring water molecules, and it's all balanced. But for the molecules that are here at the surface between the air and the water at that interface, the traction between adjacent water molecules is not balanced because there's an air molecule rather than a water molecule on the opposite side over here. Okay, so that gives rise to a surface energy along this interface, and the surface energy is it's an energy per unit area, per unit surface area. I don't know why my tablet, let's see, why my tablet has this weird, that's not what I want. Okay, so it's a surface energy per surface area, and that has the energy is force times length over length squared. So that's going to be a force per length is the surface energy between the air and the water. There also will be a similar effect here along this interface. This is, that's some kind of mineral surface when we're thinking about this in soil. And there also will be some interaction between the water molecules and the surface of the solids. And those two surface interactions are really going to be the thing that causes this effect. So to see how that works, what I want to do is to do just a simple force balance here. And the way that's going to work is that we'll have a force going this direction from the water pressure, and a force going this way from the air pressure, and then a force going that way from this interfacial tension between the water and the air. Okay, and we'll call that F. Oops. Call that FC. And I'm going to blow this up a little bit here. So blow that up. And here's that interface. So here's that interface. Here's the wall. And here's that. Hold on, I got to redraw this. Got to have a little more space. So here's that interface. There's the wall. And that's FC. The force from this surface tension between the air and the water. And that force we can resolve into a force in that direction and a force in that direction. Okay, so I'll call that FCZ and I guess FCX. Okay. All right. So the way that the force balance is going to work is that we're going to balance all the forces in the Z direction. So we'll call that Z. So we'll have a plus force in the Z direction will be FW, that one right there. And FCZ will also be going in the plus Z direction. And going in the negative Z direction would be the force from the air pressure. Okay, so that's the force balance. So we can go here and look at each one of these terms. So the force from the water pressure, that's going to be the water pressure times the area. So it's this is the area that the pressure is acting, the area of the capillary. So let's see, let me write this here. So that's RC, the radius of the capillary. So it's the pressure of the water times pi RC squared. Okay, so that gives us a force from the water. And then the air pressure is pushing down. So it's going to be the air pressure times PRC squared. Okay, so those are opposing one another. And then FC, it's from this interfacial tension. So it's going to be the interfacial tension between the air and the water times 2 pi r. And the reason for that is, I mean, we can look up here from the units. So this interfacial tension is the surface energy per unit area of the surface, but that has units of force per length. So it's going to participate in a force balance if we take it and multiply by a length. So we're going to multiply by the circumference of the inside of the pore. Okay, it's going to be, we think of it over here, see right there, it'll be the length of that circumference, you know, this, take that point and wrap it around the pore, it'll be that length. And then that FC, this arrow here, it's going to have a component that acts in the z direction. So FCZ would be 2 pi r cosine of theta, where that's going to be theta. That's theta. Okay, right here. That's theta. So theta is that angle that's formed by the interface, the air-water interface and the wall of the pore. Okay, so now we can do our balance. We can substitute these things in here. We got PW pi RC squared plus gamma. Okay, so that's just substituting things in. Now I'm going to bring the two pressures, the water pressure and the air pressure, over on the right-hand side. So that gives me this. There should be an R in there. Okay, and then I'm going to divide through by pi RC squared. And what that's going to give is this. The pi's go out, and so the pi's cancel, and the 2 is there, and cosine of theta. I think it's time for a new tab. Okay, cosine theta, and then there's the RC here. And that's going to equal the pressure atmosphere minus the pressure of the water. Okay. All right, so that's the result. We're going to call this difference between the air pressure and the water pressure the capillary pressure. And it's the pressure that results from the presence of air and water in the interface, in the pore, right? Just like what we're seeing in here. And it's pressure that's caused by these two effects. There's the interfacial tension, this gamma term between the air and the water, and then this theta term, which is the interaction between the water and the wall, the solid wall of the pore. Okay, as these two terms increase, then this term here, the capillary pressure, gets bigger. As R gets smaller, as the radius gets smaller, then the capillary pressure gets bigger. Okay, what we see too here is that if we say that the air pressure is constant and we use that as a reference, then the water pressure here is negative. Okay, and what this is essentially what's happening is that these effects here, from the FC, is causing the air pressure. See, basically, let's see. Let me see if I can switch colors here. Yeah. Yeah, I don't know. It's not. What you have here is the water pressure and then this FCZ term here are both acting in the opposite direction and opposing the air pressure. So this interfacial tension is able to have the water pressure be much less than the air pressure and still have the forces be balanced. Okay, so this is going to have an important effect though, because it means that the capillary pressure is going to be inversely proportional to the radius of the well, or the radius of the pore size, the RC. So as the pore gets smaller, then that means that the capillary pressure, that's the pressure when there's water and air in contact in the pore, that pressure is going to get increasingly negative as the pore size gets smaller. Okay, so this is called the Young's Laplace equation, and this plays an important role in establishing the capillary pressure or the negative water pressure in the Vado zone. Yeah, so there it is. There's the Young's Laplace equation. Okay, so we want to measure this capillary pressure, or measure this negative water pressure in the Vado zone. We want to determine the hydraulic head so that we can use Darcy's law. And Darcy's law is going to be just fine, that we'll have the flux equal to the hydraulic conductivity times the head gradient. So I have to be able to determine the hydraulic head in the Vado zone. So normally what we do when we determine hydraulic head is we use the water level in a piezometer. But let's just say that we put in a piezometer, and let me draw it a little bit differently here. So here's the piezometer, and it's got slots right like that, and the water level is here. Okay, so if we do that, then the water level, the piezometric head that applies right there is equal to, I don't know, we'll call that the datum. It's equal to that, right? That's what we've seen so far. and that all makes sense. And if we drop the hydraulic head, we drop the head to there, then it still works. But when in the data zone, this would be the water table down here. So if we were to drop the water table down to here, then the water that was in this piezometer would just all drain out. It would drain out through the slots, and the piezometer would be dry. Okay, so the regular piezometer design that we've seen and used, that isn't really going to work in the Veda zone. And the reason is because if the head drops below the screen, then the water will just drain out. So what you do is you replace this screen here. You know, we saw that a wire wrap screen or the plastic with the slots cut in it. You replace that with this thing here. This is a porous cup, and it's a porous ceramic, and it has very, very small pores in it, like micron-sized pores. And so what happens then is that the water wets those pores. The water can flow through those pores, but it takes very high capillary pressure for the air to enter those pores. So as the water table, if we think of this as the as the water table drops, when the water table drops from here to here, then this zone stays filled with water, because in order to drain out, the water has to flow out and air has to flow in. But if air can't flow in, then the water isn't going to flow out. So that's what this porous cup does. And as a result, then this stays filled with water, and we can measure the pressure here. The pressure here at the ground surface is going to be less than the pressure here by an amount that is equal to this height here, the pressure head. But if we measure the pressure here and then add in the pressure head from this height, we can determine the pressure head here. And this gauge is a vacuum gauge, so it's designed to measure pressures less than 0. And we can measure the pressure in the water here, and then use that to determine the pressure at this point in the porous cup, and that's the pressure head in the soil. So we determine the pressure head, and then if this is our datum, we add in the elevation head as usual, and we can use the hydraulic head methods that we've seen so far in class. So the key thing here is that we replace the screen with this porous cup. Here's a photo of these things. These are called tensiometers because they measure the tension in the water. They're designed to measure the negative pressure or tension in water in the Veda zone. So this thing up here is a vacuum gauge, and you fill this thing up with water, and then install it. And this is this porous ceramic that's in contact with the soil, and allows you to measure the hydraulic head. Okay, so we want to be able to describe water storage and change in storage in the Veda zone. And we saw when we looked at this in the saturated zone that we had porosity, and that was the ratio of the volume of water to the total volume. And when we're interested in similar things in the Veda zone, we just need to recognize that we have we've got additional constituents. So we've got solids here, and we've got the water, and we've got air, and we've got the air and the water together, which would be, so there's air, there's water, and we have both of those together, and that's the voids. And here's the solids. And we also then have a total. Okay, so we have volumes of these different components, and we have mass, and we also have weight. So we can take these various components, and they're listed here over on this side, and we can take ratios of them. So we saw this ratio before, the volume of the voids to the volume total. But we can also have ratios related to mass and weight. So the total bulk density is the mass total divided by the volume total. And the total bulk unit weight is the weight total divided by the volume total. There's another one that's important. It's called either just the bulk density, or I like to call it the dry bulk density, because it's the mass of the solids divided by the total volume, or the dry unit weight, which is the weight of the solids divided by the total volume. So those will come in handy. Density of the solids, unit weight of the solids, those are pretty self-explanatory. The void ratio, the volume of voids to the volume of the solids. Then these quantities here are going to be important to water storage. So probably the most important one for our applications is the volumetric moisture content, and it's the volume of water to the total volume, the ratio of volume of water to total volume. What's easiest to measure is what's called the water content, or mass wetness. And it's the mass of the water over mass of solids. And it's often will be determined as the weight of water to weight of solids. And then what will also be important is the degree of saturation. So that's here, and that's the volume. That's like the fraction of the pore space that's filled. So the volume of water to the volume of pores, that's the degree of saturation. And the air fill porosity will also be useful. It's the volume of air to the total volume. Okay, so these are some of the important quantities, and they're related, they're interrelated. You can go back and forth between them, and here's some of the relations between them. Okay, so we want to go and make measurements of these things, and in particular, the water content. So let's take a look and see how that's done. So the kind of the baseline method for determining the water content is using what's called a gravimetric method. And that's where you take a sample of soil, and the basic approach is to take a sample. Let's go with my illustration here. So we have a sample where we can measure the volume and we measure the weight. And then we dry it at 150 degrees C in an oven for 24 hours. That's the regulation time. And then we weigh it again. And the difference between the beginning weight and the end weight is the weight of the water that has been driven off by drying. Okay, so we can determine the water content as the change in the weight, which is the weight of the water, as a ratio between that weight and the weight final. Remember, this water content is the ratio of the mass of the water to the mass of the solids. And if you take the weights and the ratio of the weights, the gravity cancels out, so you get the ratio of the masses. Okay, so this thing here is the easiest to measure, because all you need to do is get a change in the weight between these two, and well, you need to have two weights, the starting weight and the end weight. So the difference is the weight of the water, and then the end weight is the weight of the solids. Okay, so that's going to be the easiest calculation to do because it just requires those two measurements. If we also have the volume measured accurately, then we can take the difference in the weight, that's the volume of the water, and normalize that to the volume of the sample, and that gives us the volume of water to the total volume. So that's the volumetric water content. The thing with that is, though, that in order to do this, in order to get the volumetric water content, we have to know the volume of this sample. So if it's a nice cylinder like I've drawn there, then we could calculate what the volume is. But a lot of times soil samples are kind of irregular in shape, and it's hard to get the actual the volume accurately. So when that's the case, then this method is used, the water content, just measuring the change in the weight during drying. You don't have to know the volume with any accuracy. But ideally, you've got this, you're able to measure the volume of the sample, and you can get the volumetric water content. If you know the dry unit weight and the unit weight of the water, then you can convert the weight of the water content to the volumetric water content, and using this relation here. So it's possible to do this conversion, but you have to know some additional information. Okay, so this is the easiest one, and this is the one that we want, but we need to have that additional information. So we also want to calculate some other things, the porosity. We can calculate the porosity if we know these different unit weights, the unit weight of the solids, the unit weight of the dry unit weight. So we can calculate porosity that way. The unit weight of the solids, typically what you do is use that value. That's the unit weight of quartz. And then once we have porosity, we can calculate the void ratio and also get the degree of saturation. So we can get a lot of information from just this basic test. The problem is, though, that we have to have a sample, and we've got to collect it in a way that doesn't change the volume, and then we have to get it to the laboratory to make the measurement. So that's kind of the gold standard for measuring water content. But in a lot of applications, we want to be able to measure changes in water content due to rainfall or soil drying out or a variety of things. And so there's a series of technologies that have been developed for doing this. Here are some of the examples. One of the early ones was to take a probe here that has two electrodes in it, and just put it in the soil. The water content in the soil equilibrates with the material in this probe. This is about, this is about a couple inches long. And then you measure the electrical resistance and correlate that to the water content. So that was one of the early methods. It turns out there are some factors that cause complications with that. The ion content of the water plays a big role in electrical conductivity. So it's not just the water content, but the ion content as well. So so I don't use this method really much anymore. These two electrical methods are used more these days. These are this capacitance probe. This is a commercial probe. That's kind of a pitchfork design, and that's about 3 inches long, and you stab it in the soil, and it has an electrical pulse that it puts down these prongs and measures the capacitance of the soil, and that is proportional, or there's a you can get a correlation function that works pretty well that relates the capacitance to the water content. Here's another pitchfork looking probe, and you stab it in the soil and then use this device to measure essentially like the capacitance. So those allow you to hook these probes up to an electrical device and measure the change in the water content with time to log it. Here's another device. This thing is a neutron probe. That's the probe there, and it goes in a borehole. And this works a little bit differently. This probe here has a radioactive source in it that shoots neutrons out, or that has neutrons shooting out of it just from the radioactive decay. And what happens is that when neutrons are being emitted, the neutrons hit other atoms and they recoil off of those atoms. And the amount that they recoil depends on the mass of the atom. If the mass of the atom is similar to or molecule, is the mass is similar to a neutron, then it works like, you know, two pool balls hitting. When the cue ball hits another pool ball, then it transfers a lot of the kinetic energy into that other ball if the masses are the same. But if the cue ball in pool hits a bowling ball, you know, it doesn't really transfer much energy. So what happens is that the hydrogen in water is similar to the mass of a neutron, a little bit more, but it's the closest of the atoms. And so depending upon the hydrogen content, that affects the scattering of the neutrons from this radioactive source. So there's a neutron detector here that detects how many neutrons get scattered back, and that's used to determine the water content. So you can lower this thing down and measure the water content as a function of depth. So that works pretty good. It's a probe that you can lower down and get profiles. But you know, you have to have a radioactive source in this thing. So that's kind of complicated to have around logistically. You have to have a special permit to have a radioactive source. So these things are used, but they're you don't see them around all that much. This thing right here, this is probably the most common water content monitoring device out there now. This capacitance probe costs, I don't know, a couple $100 and hooks up to a little electrical device that you can use to monitor water content. Okay, so we want to look at how water gets released from storage in the Veda zone. And what I want to do is go through an experiment where we've got some soil here in a cup, and the bottom of the cup is we've got a plate here and then a tube, and we start off with the water level up here equal to the level of the sample. Okay, so this sample is now saturated, and we can presumably we know what the saturated water content is. And then I'm going to drop this tube down. So you can see here it's dropped down. It dropped down to here. Let's just say we drop it down to here. This applies this much suction head to the soil. And so what happens then is we pull water out, and and the water level rises back up. And then we take the tube and we drop it back down to here. We measure this distance here. We then drop this tube back down to here, and it rises up a little bit more, and we measure that, and then we return it back to this level. And eventually we have it at this level and it's stable and no water is coming out. So we take these measurements here and we determine how much water is removed from the soil when we apply this much suction. Okay, and then we plot that up. So here's the water content as a function of the applied suction. So we start here at the saturated, and we apply this much suction head, and we get a value here because we've pulled out that much water. Okay, that's the amount that we calculate here. And so we've reduced the suction, we reduced the water content by applying that much suction. Okay, so that's an experiment that we run to get the water content as a function of suction. There's some interesting things that happen when we do this, but that'll require a little more explanation that I think I'll bring up, I'll start with next time. Okay, so I'll see you on Wednesday back in the classroom, and good luck with the experiments. And actually, Joey, if you're still on, could you give me a call? My number is 864-356-8349. Let's try to work out this.
Sure, but I mean, if we stay in the Zoom meeting, we could just
Okay.
talk
Yeah,
with the
that's
other
fine.
group members here.
Yeah, okay, that'd be good.
If you don't mind me going first, I had a question about the test.
Sure.
Yeah, go ahead.
So on Canvas, I see we're supposed to also test CBW1U and CBW1L. I know you mentioned this in class, but there's just not a map of it that I found, so I didn't know if you could help me
so
direct to do it.
Yeah. There's a new map. I revised the assignment, so check on the Canvas. There's a new map. They are indicated with a flag, so you should see them.
Okay. I'll check that. I took a screenshot of the slide you had at the beginning of class.
Yeah, here,
I think I might see it there. Is that in the north east corner?
Can you still see the screen?
Yes.
Okay, so we were parked right here. We came in this way. So CBW is right there. And there are two of them. There's an upper and a lower. And you need to use the water level meter to drop it down to the bottom and see which one is deeper. That's the CBWL. Okay, so do a little bit of detective work. But you should be able to, there should be a flag there. So, and you should see two of these wells. They're about, I don't know, 8-10 feet apart.
Okay.
So from here to here is 100 feet. And then from here up to CBW4 is 100 feet.
Okay. Thank you. I appreciate it.
Yeah. You should be able to see the flags from them.
And then for time, as you mentioned, I would assume we should test the water levels first and then do the slug test afterwards so that we can try to, like, in case the other group shows up and we are behind, we can just cut our test off then.
Yes, but also you want to measure the water levels before you start doing slug tests, because the slug test change the water levels.
Yeah, the baseline.
Right.
Okay.
Yeah.
Thank you, sir. I appreciate it. Sorry to keep everyone else.
It's okay.
All right. Take care. Thank you.
So you're still there, Joey?
Yeah. I think everybody in our group is here. Also, Dom was mentioning that his group has had some trouble scheduling things, so he would also be able to switch into ours.
That's right. Yeah.
So from
Okay,
the
well,
start, we were planning to meet at 3:30 today. Somebody in our group had a problem come up with that, and I was first just wondering if I could see the list of everybody's time slots to see if there was anywhere we could fit in where there weren't other
yeah,
groups testing.
yeah. So I put that in Dom's notebook and he sent it to me. So
Okay.
let me get it here.
I mean, I think if Dom could switch to our group, then our group member that has a scheduling conflict could switch to the 1:30 group, and then we could still have enough people to do the test.
Okay, so you can see that.
So we were the 3:30 group. Let's take a picture.
Okay. So Dom, have you heard from your group?
Yes, but the only thing with that is, with me being a graduate teaching assistant, I don't really have much free time. So I think today is probably the best day to work for me. Otherwise, I'd have to be canceling office hours and running back and forth between campus to make my labs. So that's why I was hoping to do today on Monday, but Joe said he can do tomorrow at 11 a.m. Lewis is not available tomorrow at 11 a.m. But the only issue with doing it at 11 a.m. is I would have to cancel office hours on campus. I was trying to avoid doing that if possible.
Okay.
So if I do go with Joey's group, I would need to help my group figure out how they
Right,
can get some data.
right. So nothing works on Wednesday?
Um, I mean, the only thing that I could think of that would work is if I get out there early, like 7:30 a.m., 7 a.m., but I don't think anybody's gonna want to do that. So
So Joseph, what group are you in?
He's in group
I'm
2, our group.
yeah.
So you're in the group with Joey?
Hmm.
Okay. So Dom, you're in the group with Lewis and
Joe and Camille.
oh, okay. Have you been in touch with Joe?
Joe said he can do tomorrow at 11 a.m., but if I need to do that, I'll do that with Joe. But I have a class that I need to teach at 1:20 on campus. Then I have office hours from 11 to 12, so I'd have to cancel office hours, which I can do, but I would have a time slot free from 11 to 1, 11 to 1 o'clock in that case.
So how much, I mean, what kind of office hour attendance do you usually have?
Pretty low. It's almost non-existent.
Yeah, so maybe do that, but Lewis can't make it, huh?
Lewis cannot make it, no. He said he has class from 11 to 4:30 or something like that on Tuesdays.
Okay. I wonder whether he could make it with the Wednesday group. So
Yeah.
Joey, so Luke and Joseph, those are your two other group members.
Yes. I think wasn't there one more person?
Who, there was somebody that can't make it today, right?
Yeah, that's Dr. Burke. That's me. This is Luke. I apologize for the inconvenience. I have my advising appointment at 3:45, and I was scheduled to do it at 3:30 today. And was just wondering if I can possibly join another group, maybe the 1:30 group today.
Okay.
Um,
Okay.
I don't know
I mean,
I could maybe trade with Dominic. I don't know, Dominic, what time were you scheduled to?
Just thinking 11 a.m. tomorrow, if
Okay, I
you're
have a class at
available.
11 a.m., but maybe if there's someone on the Wednesday at 2:30 group.
Either that or, I mean, we could try pushing our start time to 4 p.m. and then Luke, you could just get there whenever you could. I probably wouldn't want to start much later than 4 because I think sunset's at like 5:30 or something like that with the time change.
Right,
I'd rather not be out there doing tests in the dark,
right.
especially if they close the gate,
How-
which I know that they do tend to close the gate in the evenings.
Yeah. I don't. I mean, we have the combos, so we can get you out of there. So Luke, how long do you think the advising meeting is going to be?
It's from 3:45 to 4:15.
Okay, but then you still have to get out there, right? So it'd be like 4:30.
Right.
Yeah. Okay, well, yeah, it sounds like maybe it's going to be better if you go. So if you go at 1:30, then that leaves. Well, I don't know. I guess what would be good is if, well, with the folks who are here, having Joey and Dom and Joseph go at 3:30, and Luke, you go at 1:30, and then
Okay.
Joe and Lewis. I mean, those guys, neither of them were here. That's the problem. So they don't really know what to do. And there's only going to be that Wednesday group that they're going to be able to get in on.
Let me reach out to them and just let them know what my thinking is, and I mean,
So
I'll give them the schedule and see if they can link up with those other people in the other groups, I guess.
so Luke, you know Lewis, right?
Yes.
So can you get with him and see if you guys could, if you could do it sometime with him? Because
Sure.
he wasn't there, so he doesn't really know what to do. And the way it's shaping up, he and Joe, who also wasn't there, are the kind of the two people that we're trying to place in a time slot. But we need to have somebody that was there and knows what to do.
Yeah.
Right.
So I don't know. You think you can get him fairly quickly? Because if you're going to do the 1:30 time slot, then there's not much time left.
Yes. I'll call him shortly. I sent you an email. Is that a good way to communicate with you?
Yeah, or call.
Okay. Sounds good. Then I'll just call you. I'm sorry, could you repeat your phone number one time, please?
Yeah, it's 864
Okay.
356 8349.
Okay, sounds good. I have you saved. Thank you very much. I'll give you a call when I hear back from Lewis.
Yeah, okay. You still there, Luke?
Yes, I am.
Does that Wednesday time work for you as a fallback in case this, because if we give up the 1:30 time slot, that doesn't leave anything else until, with other groups until Wednesday.
Yeah, I think I could do that one.
Okay. All right. We'll have that be a fallback.
Okay, sounds good. Thank you very much.
You bet. Okay. And Dom, you're going to try to get with Lewis too, and Joe.
I'm gonna message them, but I can either do today at 3:30 or 11 o'clock tomorrow. Otherwise, I can't do any of the other time slots. And I don't want to. Wednesday, I have a lab, a 3-hour lab, so
Right.
I'll message them. But if I can't figure it out with them, I'm probably gonna just reach out to Joey and try to work with
Yeah.
Joey today.
Yeah, that would be okay. That's
Okay.
fine.
Okay, sounds good.
Yep.
Great.
Yep. All right. I think that makes sense to do. Very good.
All right.
Well, let me know how things evolve. But I guess Dominic, you and Joey and Joseph will be going today. And Luke, yeah, if you can work something out with Lewis, that would be ideal. I mean, just the two of you could do it together. If it doesn't work out with Joe. So yeah, let me know how that goes.
Will do. Thank you very much.
Good luck, guys.
All right.
Thanks.
Thank
Yeah.
you. Have a good day.
Thank you.